All right, people, we're going through the combined science 2024 GCSE chemistry, AQA, 8 questions. Let's go. Copper is a useful metal. This is question one. I suggest at the start of each question, you pause the video and have a go. Let's try and get this in frame. Otherwise, there's no point in you being able to have a go at it. So it says 1.1, figure one shows the mass of copper produced between 1900 and 2010. Give two conclusions that can be made from figure one, 2 marks. So whenever you get these, describe the graph, give two conclusions from the graph. They just want you to state facts. Okay, and you'll get 1 mark for the general relationship and then 1 mark for a more nuanced, a more specific statement about a slight trend in the graph. So look here, as the time goes on, as the years increase, the mass of copper produced goes up. So there's our first mark, really easy one. So as time increases, or as the years increase, so does the mass of copper. Now, it's nicer to write the mass of copper produced each year and as years increase, but I've just gone for that. As time increase, so does the mass of copper. Right. Now we need to look at the more kind of, for the second mark, a little bit more detail. Look at the shape of the graph there. It's steeper there and it's slower here. So we want to say at first, maybe between 1900 and 1950 or 1900 and 1925, there's a steady increase. So I'm giving it a little bit extra. So between 1900 and 1925, we've got a steady increase. Now, look, I could say between but I'm just going to go here, 1950 to the present day. From 1950 onwards, there's a rapid increase from 50 onwards. Oh my gosh, can't spell onwards, a rapid increase, right? So first mark's always for a general relationship. The second mark is for you to check where the curve, the line bends, slows down, goes steeper, and point that out, okay? There's no explanation needed. We don't need to say from 1950 the human population is increasing massively. We need the demand for copper is increasing for electrical wiring, for cooking pot. You don't need to put any of that. There's no word explain. That's what you do when you get an explain or suggest. Okay, let's move on. Enough of my whiffle waffle waffle. We want to get through the paper quick, smart, quick time. Mixtures of copper and zinc are heated to produce alloys. 1.2. Figure 2 represents the structures of pure copper and of the alloy copper and tin. No, copper and zinc. I can't read. Here is the structure of pure copper. Here is an alloy of copper and zinc. Explain why the alloy of copper and zinc is harder than pure copper. So this is worth 3 marks. Why is this one harder? And there are 3 distinct points you've got to say. You need to learn these off by heart. It's a real common question. Put it on a revision card. Why don't you pause the video, grab your pen, paper, have a go. Okay, here are the answers. Right, you can see there, alloy made of different elements. Ooh, elements, right? So it's got copper and zinc, different elements. I want to say they are different sizes. They disrupt the layers. You see, like the pure one is arranged in layers. This one has disrupted layers. And then we say the layers cannot slide. So I've made 4 points to get my thing across. Said, look, there's different elements that are different sizes. That's kind of 1 mark. Elements of different sizes. They disrupt the layers. The layers can't slide. That's your 3 marks for learning why alloys are harder. If you're ever asked why is copper softer, you say it's made of one type of element, all the same size, in a regular arrangement, in layers. The layers can slide. Anywho, let's move on. We don't want to waste all your day. 1.3. There's a number of ways to do this question. 5.25 grams, I can't read, sample of an alloy of copper and zinc contains 13.5% zinc by mass. So 13.5 of that is zinc. Calculate the mass of copper in the 5.25 gram sample. Listen, you can do it 2 ways. We can either work out the mass of zinc and take it away from the total, or we can work out the mass of copper. So I'm going to give you one way to do it. One way to do it is to say, well, it's 100% zinc and copper, right? But we know that the zinc is 13.5. So I'm going to take 13.5% away from 100%. And what is that going to give? That's going to give me the percent of copper. So minus woo, 100 minus 13.5. And that's going to give me the percentage of copper, and the percentage of copper is 86.5%. Look, that's how I did it. 100%. I took away the 13.5 for the zinc, and that left me with the copper. Why? Why, you ask? Why? Because this is copper plus, oh my days. Anyway, yeah, the 100% is copper plus zinc. The 13.5% is the zinc. So if I take that away from that, I get the copper. Now all I need to do is find out what is 86.5% of 5.25. You can do this a number of ways. Easiest way is 86.5 over 100. I can tell you now. And then you're going to times that by 5.25, and that's going to get you another mark. So we're going to go bish, bash, and then we're going to get bosh when we get the other mark. So divided by 100, that equals 0.865, times that by 5.25, and we're going to get 4.541. And so that's going to get you a third mark, which is 4.541. Now it said, pay attention to the bulb, mass of the copper, 3 sig fig. So we need to do this to 3 significant figures. So it's 4.54. Why is it not 4.55? Because the 1 is lower than 5. So we keep this at 4. And there we go. That's your other 2 marks for a lovely 4 marks. Right, let's move on. There's a number of ways to do that previous question. Okay. And question 2, a student prepared copper sulfate by reacting acid with excess copper carbonate. Figure 3 shows the first 2 stages in the preparation of copper sulfate. So what we have here, we have copper carbonate going into a beaker with acid. So there's going to be a reaction. Now we have copper sulfate solution and some unreacted copper carbonate, some of that reactant left over. What are they doing here with this equipment? And then we got the copper sulfate solution there. Okay, let's zing down. What is the formula of the acid used to prepare copper sulfate? If you want to make a sulfate acid, right, you need if you want to make a sulfate salt, you need sulfuric acid. If you want to make a chloride salt, you need chloric acid, hydrochloric acid. If you want to make a nitrate salt, you need nitric acid. If you want to make a phosphate salt, you need phosphoric acid. So you get the idea. Which one of these is the sulfuric acid symbol? It's this one, H2SO4. That was nitric acid. That would make you nitrate salts. That's hydrochloric acid. That would make you chloride salts. Anywho, let's move on. Right, 2.2. Why is excess copper carbonate used in stage 1? So if we go back up here to the picture, maybe you could pause the video, have a little think about this one. Why did they use extra copper carbonate? What did they want to make sure had happened by using extra copper carbonate? They wanted to make sure that all of the acid had reacted. And you see here afterwards in stage 2, there's no acid in there. It's just salt, which they made from the acid and the carbonate, and excess copper carbonate. So we always had excess to ensure that all the acid has reacted. So to ensure all the acid has reacted, yeah, it's the sulfuric acid, but we don't need to put that. Okay. Oh, big yawn. 2.3. Beaker N contained copper sulfate solution. Describe how the student could produce copper sulfate crystals from the copper sulfate solution in Beaker N. Let's go check out Beaker N and then get back to this question. Pause the video, have a go when you get a chance. Here's beaker N. What have they done here? They filtered off the unreacted copper carbonate. They filtered off the excess. You always do that because you don't want that with your salt. Now we've got just salt and water. How do I get the salt away from salt and water? Pause the video, have a think. Okay, there's 2 kind of key words here. It's evaporation and crystallization. So I'm going to say heat gently. Don't use a Bunsen burner. You could use a water bath. You could use an electric heater because you can, whoops, you can set an electric heater to a gentle heat. Okay, it's difficult to control the heat with a Bunsen burner. So heat gently using water bath, electric heater, evaporate some of the water. Then what do you want to do? Then leave to crystallize in a cool place. So then we leave it to crystallize. And that will get you the 2 marks. The key words here are evaporation and crystallization. Okay. Evaporation and crystallization are slightly evaporation, you're heating the water so it goes. Crystallization, once you get a few crystals form, more crystals come out of the water. So you're just leaving it to the side for more crystals to form. All right, let's go. Let's go. They're slightly different processes. Okay. A student investigated thermal decomposition. Think about that word thermal. It means heating. Decomposition means breaking. So breaking something with heat of copper carbonate. Copper carbonate decomposes, breaks to form two products. Figure 4 shows the apparatus. We've got a test tube here. We've got a heat source. We've got 1.2 grams of copper carbonate in there. Now, this is the method they used. Add 1.2 grams of copper carbonate to a test tube. Heat the test tube and the contents until the mass does not change. Heat until a constant mass. That's a good thing. Record the mass of the contents and the test tube after heating. Repeat steps 1 to 3 with different masses of copper carbonate. Nice. Okay. Table of results, mass of the copper carbonate before heating, mass of the copper carbonate after heating. So 1.2, 0.8, 2.4, 1.7, 3.6, 2.2. You get the idea. Plot the data on plot the data from table 1 on figure 5 and draw a line of best fit. So I'm going to go ahead and do that. Give me 1 secondo, peeps. Oh my days. I just need to get the table up at the same time. Okay, so we need to just plot this data on, which is the mass of copper carbonate in the test tube before heating to the mass of the contents after heating. So let's do it. This is the mass of the contents of the test tube after heating, mass of the in the test tube before heating. So they've done a bit of a whoopsie here. This is very unusual and kind of designed to trick you. The mass of the copper carbonate in the test tube before heating. Normally, yeah, that's the independent variable. That's fine. The independent variable is always in the first column. That goes along the horizontal x-axis, and this always goes on the y-axis. Anywho, you can just match up the names, but I'm sure a few people made mistakes here because it's mass and mass, so it's a little bit confusing. So anyway, first column along here, so I want to go to 1.2. What you've got to do is find out what each square is worth. So there are 10 squares there, and the division, the value is 1, so it goes up by 1 each 10 squares. So you do 1 over 10, each square is worth 0.1 per square. And luckily for us, they got the same value going up there, which makes it a lot easier. So we want to go to 1.2. So we go 2 squares along, and then we go up to 0.8, which is here. So 0.8 there and 1.2. Now we go to 2.4. That's 4 squares along, and we go up to 1.7. Oh my days. There's 1.7. Bada bada bing. Now I want to go to 3.6. So we go here 6 squares past 3, and we want to go up to 2.2. So 2.2 is there roughly. Now, excuse me, you're allowed to be half a square out, so don't panic too much. 4.8 and 3.1. So I want to go 4.8 and I want to zing up to 3.1. And so that is about there. Looks a bit weird now, getting a bit strange. And then 3.9 and 6. So we go to 6 and we go to 3.9. So we go all the way up here, 6 and 3.9. Now we need a line of best fit. It's not really a curve. I'm just going to do a straight line here. If it was a curve, there'd be more of a natural curve. But what I can do here is I can go as close to all of those points as I can. I'm going to go all the way to the end of the graph like that. And there we go. That is going to get you your 3 marks. 2 for the plots, 1 for your line of best fit, going through as many of the points as you can, as close to all the points. There we go. 3 fat marks. Right, let's move on. Why does the mass of the contents of the test tube decrease in mass when copper carbonate is thermally decomposed? What do you think happens during the thermal decomposition of copper carbonate? Do they tell us? No, but hopefully you actually know the answer to this, and I'm going to draw it out. It's a reaction you can draw out. So copper carbonate looks like that, CuCO3, and if you heat it, it breaks down into copper oxide. Copper carbonate's green, copper oxide's black, and it gives off carbon dioxide. What do you know about carbon dioxide? it's a gas, and that is what it escapes the test tube, and that's why the mass goes down. So we can say carbon dioxide gas is given off. Um, and it has mass. You don't need to do that. You can just say CO2 is coming off. But basically, carbon dioxide is a gas. Gases have mass, so it's losing mass as the gas escapes. Why does it escape? Because there's no lid on it, and you wouldn't put a lid on it because that would be pressure buildup. Right. Anyway, let's move on. Enough whiffle. We're on question 3. Table 2. It's the 6-fat marker. Boom! Shows diagrams which represent the structures of 2 substances. So we've got 2 substances here. Hopefully, looking at that minus and that plus, minus, plus, minus, plus, minus, plus, kind of recognize what type of particles have a minus in them and the plus in them. This is sodium chloride and this is oxygen, and there's no minus or plus in the oxygen. Compare the structure and the bonding of the sodium chloride and with the oxygen. So we've got 2 instructions here. We need to talk about the structure of sodium chloride and the bonding in sodium chloride. We need to talk about the structure in oxygen and the bonding in oxygen. Now you could just talk about all of the sodium chloride first and then say whereas in the oxygen this. I'm going to go bit for bit, but you don't have to. So sodium chloride, you should be able to ask yourself, this is a metal. This is a metal and non-metal. No more clues, peeps. You've got to do this yourselves. And oxygen is a non-metal. So why don't you pause the video, grab a pen and paper, see how many marks you get. All right, let's go through it. Right. I'm just going to put everything that I would put down and then we'll check the mark scheme. So sodium chloride, right? For me, sodium chloride is an ionic compound. It has ionic bonds. It has a giant, keyword, ionic structure. You can call it a macro molecule, a giant ionic lattice. People love that one. There's all of those are the same thing. But the key words here is that it's got ionic bonds and it has a giant structure. So there's 2 parts there. Now, what do we want to say? I'm going to give you the definition of an ionic bond here. Okay, so an ionic bond is a strong attraction between oppositely charged ions. So I'm telling the examiner that I know this is made up of ions of opposite charges, plus and minus. I know that it's a giant structure, lots of ions, and I know that it has ionic bonding. So that's everything I need to know there. Now, if I want, I could say this makes it hard, but it hasn't really told me to talk about the properties. It's just they compare the structure and bonding. But knowing me, if I was in an exam and I got 6 minutes, this has taken me 1 minute, I would just bust out, yeah, the very strong, lots of strong ionic bonds need lots of energy to break, hence it's hard and it has a high melting point. That's just because I like to get in that habit. Okay, let's go into oxygen. They're never going to take marks off you for that. So whereas oxygen is made of non-metal atoms, that are covalently bonded. So I've mentioned the bonding. Now I need to talk about the structure, and it has a simple structure. Okay. It has a strong covalent bond. So, it has a strong covalent bond, which is the attraction between shared pair of electrons and nuclei. Okay, I could mention that the nuclei are positive if I want to point everything out. However, here's my however. There are no bonds between the molecules of oxygen, just weak intermolecular forces. So the difference is that whereas the giant ionic structure has bonds everywhere, okay, the oxygen is like this. So very strong double oxygen bond there, whatever that is, 498 or something. It's a lot of joules of energy to break these bonds. These are strong covalent bonds. However, there are only weak intermolecular forces between, which is why oxygen's a gas and which is why sodium chloride is a solid at room temperature. This is in a giant structure. Anywho, that is all your fat 6 marks. Boom! Right, let's move on. How did you do? I hope you did all right. Let's zing. We're on question 4. Let's go. Nitric acid is a strong acid. What's meant by a strong acid? Pause the video, have a go. Okay, the biggest misconception here, guys, is people are going to say, oh, it's got a low pH. Now, generally, strong acids do have a lower pH than weak acids if they're of the same concentration. However, what a strong acid is, you need to know this definition off by heart, so I suggest you put it on a revision card. It fully ionizes in water or in solution. I'm going to put in solution. You could put in water. So it fully ionizes in solution. Now I'm going to show you an equation to show what that means. That means if you have hydrochloric acid and you put it in solution, the old AQ, then it is going to split into hydrogen ions and chloride ions. There will be no HCl actually left. So if I had a glass of hydrochloric acid mixed with water, the hydrochloric acid will be split, all of them, into hydrogen ions and chloride ions. There won't be any HCl joined together left. They all will all be moving around each other like that. And so it fully ionizes, fully becomes ions. If it's a weak acid, it partially ionizes. Anywho, 4.2, nitric acid used as a dilute aqueous solution. What is meant by dilute aqueous solution? It just means a low concentration of the acid. It is in a large amount of water. It's dissolved in a large amount of water. So if you dissolve a little bit of acid in lots of water, you get a dilute concentration. So a low concentration of acid, a low concentration of hydrogen ions will be released. Okay, let's zing on. Oh my days, ticks flying out. Come on. 4.3, 10 centimeter cubed of a nitric acid solution has a pH of 1. Water is added to the nitric acid solution to change the pH of the nitric acid solution to pH 3. How does the hydrogen ion concentration change? Why don't you pause the video, have a go? Okay, folks, I'm going to go through the answers, obviously. So pH, some people think it stands for power of hydrogen. I've never really found out what it means. But pH, yeah, you could think of it power of hydrogen. So pH 1 is a stronger concentration. pH 1 is actually 0.1 mole per decimeter of hydrogen ions. pH 2 is 0.01 mole per decimeter, and pH 3 is 0.001 mole per decimeter of hydrogen ions. So with each increase in pH, when I go from pH 1 to 2, I actually get 10 times weaker. The concentration gets 10 times weaker. So you divide by 10 the concentration with each time you go up. So guess what the answer is for this one? You're going to divide the concentration by 10, then divide by 10 again. It decreases by a factor of 100, 10 by 10. Now the opposite, if you were going from, if the question said we're going from pH 3 to pH 1, how many times stronger is it? Well, it would increase by a factor of 10 times 10, which is 100. And of course, if I put 4 in there, then, and I said, how much does the concentration increase if it goes from pH 4 to pH 1? It would increase by 1,000, 10 times 10 times 10. You get the coup. As we go up, we get 10 times weaker with each pH. As we go down the pH scale, we get 10 times stronger. Now, that is the hydrogen ion concentration we're talking about there. Of course, acids release hydrogen ions. Right, enough whiffling. Write the ionic equation for the reaction between any acid and any alkali. It's just H plus. I'm not going to put the state symbols. Everything should be AQ if you're going to put state symbols. It's H plus OH minus and goes to H2O. That would be liquid. If they ever ask for state symbols, actually, the water can't be aqueous because aqueous means dissolved in water. So water's liquid. Anything else that's with the water, yeah, these are in solution. So anywho, there we go. Mark, move on. Let's go. Learn that off by heart. Put it on a revision card. Hydrogen ions are released by acids. Hydroxide ions are formed when bases react. The equation shows the reaction between magnesium carbonate, that's a base, and nitric acid, that's an acid. So it's a neutralization reaction. What is the ratio of the number of moles of magnesium carbonate to the number of moles of nitric acid? Well, let's check it out. Here's magnesium carbonate, and there's the nitric acid. What's the ratio? Well, there's no number in front of that, so we just presume it's 1, and there is a 2 in front of that, so it's 1 to 2. Lovely. Nice and easy. Like that one. Let's hope chemistry stays that easy, eh? A student mixed the magnesium carbonate with excess nitric acid. The student then added 2 drops of universal indicator solution. What color was the solution? So we had magnesium carbonate, but we've got extra acid. If it's extra acid, then overall what's left? Acid. So it means all the alkali, the base, has gone and we're left with the acid. If you put indicator in an acid, what color is it going to go? Red, green, or blue? You should know this, guys. It's going to be red. Okay. So, yeah, green is more neutral. Some alkalis are green, and then blue is an alkali. Purple is very strong alkali. Okay, zinging down. A student investigated the temperature change when different masses of magnesium carbonate were reacted with excess nitric acid. Figure 6 shows the apparatus. Here's figure 6. 0.50 grams of magnesium carbonate added with a spoon or spatula into this beaker. Actually, it's a polystyrene cup. We've got to think, why are they using a polystyrene cup? And they've got a thermometer, so they're trying to measure the temperature. And we got 50 centimeters of nitric acid. So we're doing a neutralization reaction, magnesium carbonate and acid. This is the method used. Pour 50 centimeters of nitric acid in the cup, bosh. Measure the temperature, lovely. Then add the magnesium carbonate, 0.5. Stir it and measure the temperature again. 6, repeat steps 1 to 5 with different masses. So we want to see, how does it affect the temperature change when we use different amounts of magnesium carbonate? Give 2 improvements to the method to produce more accurate results. Do not refer to improvements to the apparatus. So we're not allowed to say improvements to the actual apparatus. Okay, well, let's have a look at their method. We're not allowed to say improvements to the apparatus. Otherwise, I would have said put a lid on the polystyrene cup, right? Prevent heat loss. I would have said use a digital thermometer, but we can't do that. So, what we want to go through here is improvements to the actual method. So, let's think about the method here. They did the experiment, but they did it once for each mass. So I would say repeat 3 times for each mass and calculate a mean. So we want to repeat 3 times and calculate a mean temperature. We could say discard or get rid of anomalies, which means odd results. Now, the other thing they did was they just measured the temperature. They should have measured, say, they should have measured the temperature for every minute until the reaction was complete and then recorded the highest temperature. So record the temperature for every minute for 5 minutes and note the highest temp recorded. So what I'm saying there is when you carry out the reaction, it might have gone from 25 degrees up to 35, but if we checked a minute later, it might have gone up to 55. So surely you want to wait and get it to go up to 55, and then it starts coming back down. You go, right, that's the highest temp. That's the biggest temperature change. They just took the temperature straight after. Now, that's not necessarily going to be the most accurate way to do it. Okay, let's move on because that's the end of that question. Question 5. Nitrogen reacts with hydrogen to produce ammonia. Complete the dot and cross diagram for an ammonia molecule. 2 marks. Why don't you copy this down on a scrap bit of paper? Have a go. This should be bread and butter for you guys. All right, I'm going to go through the answers. So hydrogen is essentially like a group 1 element. It has 1 electron. So I'm going to bus out hydrogen's electron here in the space, the overlap between these non-metals. And then nitrogen is in group 5, so it has 5 electrons. Hydrogen only wants 1, can't take any more than that because it's only got a little shell and it fills up with 2. And that means that nitrogen has 2 left over. They should really be on the ring, but I'm not that accurate. Okay, there you go. Lovely. How did you do? Both marks? Hope so. Let's go. Don't forget to hit the like, share, and subscribe, peeps. It massively helps me out. 5.2, the equation for the reaction between nitrogen and hydrogen to produce ammonia is N2 plus 3H2 goes to 2NH3. Calculate the mass of hydrogen that's needed to produce 25 grams of ammonia. They've given us the relative atomic mass. So they've given me mass and they've given me like MR. And as soon as I see that, I think to myself, we're doing this, peeps. We're doing mass. I don't know how you remember this, but some people say mass equals Mr. Moles. MRAR, same thing. We're not going to worry about the difference between that. So I've got that and that. So where am I starting here? This is a slightly unusual reacting mass question. It's 4 whopping marks. We're starting with the ammonia. Can you spot the ammonia? What are the names of these things? So hopefully you've realized N2 is nitrogen, 3H2 is hydrogen, and NH3 is ammonia. So we're starting at the back, and then they're saying, what is the actual question is asking for the mass of hydrogen. So we're looking at this to this. Let's start off and calculate what we can. So you should be able to go, that is ammonia, NH3. Let's find out how many moles we've got, because I've got 25 grams, which is the mass, and I want to do mass over MR is going to give me the moles. Now, what's the MR of ammonia? Well, 14 for the nitrogen, and there are 3 hydrogens, so a total of 17. So 25 divided by 17 is going to give me my number of moles. Let me bust out the calc because I ain't good enough to do that with the old brain skills. So 1.47. It's 1.4705. I'm leaving it as 1.47. There we go. That's my moles. Now I want to note down what I've just calculated. That was ammonia. There we go. They're my moles of ammonia. Now the next step is to look at the ratio. The reason why you balance equations, or they give you these equations, it's always they want you to use the ratio in every mole one. So we're going from 2 ammonias to 3 hydrogens. So the ratio is 2 to 3. So what do I have to do in my calculator to go from 2 to 3? Well, I times it by 1.5. So if I times this by 1.5, I'll be increasing it by 2 to 3. You can go 1.47 and you could divide it by 2, times it by 3. That's what some people do to do the ratio. I'm just going to times this by 1.5. And that is going to give me 2.2058 moles. 2.2058 moles. Now, what have I just calculated? That is how much hydrogen we've got. Now I need to put it back in here. This will have scored me 3 marks. So I'll get a mark for that, mark for the ratio, mark for that. Now I need to smash this back in and get the mass. So I've got the MR. The MR is actually going to be H is 1. I've got 2 H's. So I'm going to do this times 2, because 2 is the MR of hydrogen, times that by 2, and that gives me my mass. And my mass is going to be 4.41. There we go, 4.41. Lovely jubbly. All right, folks, that will get you the 4th mark. Right, let's zing. Figure 7 shows the displayed formula equation for the reaction of nitrogen with hydrogen. We've got nitrogen, we've got hydrogen, we've got ammonia. In the reaction, the energy released forming new bonds is 93 kilojoules, greater than the energy needed to break existing bonds. What this is telling me is that overall, 93 joules of energy is released. And that means it's minus 93. So little clue there. They told us that by telling us energy released is 93 more than went in. So it's minus 93. They want me to calculate this missing HH bond. We've got this table. Calculate the bond energy X for the HH bond. All you have to do normally to work this out is do the reactants, which are over here, minus the products. So all I'm going to do is work out the numbers here. Obviously, I don't know this, so I'm going to leave this as 3x. I turn this arrow into a minus, use that number equals minus 93, rearrange, solve, boom, 5 marks. Right, let's go. So I've got 945 over here. So we got 945 for this plus 3 times x minus, woo, that number. So I've got 391. This will confuse a lot of people. There's 1, 2, 3 of these 391s, but there's also a multiplier here. And this is like saying 2 times 3 times 391. So you could just do 6 times 391, right? Because they're saying you have NH3. What does that big 2 mean? That big 2 means there are 2 lots or 2 times NH3. And that means you have 1, 2, 3, 4, 5, 6 of these. So we're going to go 6 times 391. And I smash that in the calc. 6 times 391. And that equals 2346. So it's all a bit messy looking up here. So I'm going to do this down here where I've got a bit of space. So the equation I want you to solve is 945 plus 3x. Remember, we're trying to find x here. Take away 2346. You always put a take away where that arrow is in these equations. And that equals minus 93. So what I want to do is shift things over to both sides and sort it out. I could just put the 945 onto that. So I might do that to start with. Let's go. We've got minus 2346. Okay. Plus 945. That's going to give me, if I simplify, I'm going to get 3x minus, what is that? 1401. Oh my days. Minus 1401 is equal to minus 93. Now what I could do is just add, I want to get rid of the 1401. So I'm just going to add 1401 to each side. So I'm going to go minus 93 plus 1401. Or I could say minus 93, yeah, plus 1401. And that is going to get me 3x is equal to 1308. Now, what did I do? I added 1401 to each side, right? I wanted to add it to each side to get rid of that, cancel that out and leave 3x. What did I do here? I added the 945 to the minus 2346 because they're in the same kind of number, so I can get rid of, simplify that. Now I have 3x equals that. I'm going to go divide that by 3 and I'm going to get 436. So divide this by 3 to find x. X is equal to 436. 5 marks. Ah! All right, let's move on. Right, 5.4. Energy is, ooh, I can't see that properly. Okay, 5.4. Energy is released from the reaction to produce ammonia. Figure 8 shows part of the reaction profile for the reaction between nitrogen and hydrogen to produce ammonia. Complete figure 8. You should complete the profile line, so I need to complete that. Label the energy level of the reactants and the products and label the overall energy change. Right, so this is an exothermic reaction. It gave out minus 93. That means that at the end, the products are lower. So make sure you've had a go at this. I always forget to say pause the video every time, but it gets a bit boring, doesn't it? So those are your reactants. These are your products. The products are going to be lower because it's an exothermic reaction. The reaction always has a bit of a hill because it has an activation energy. They haven't asked us to label that, but they have asked us to label the overall energy change. Now, the overall energy change is going down because it was minus 93. So this is the overall energy change. So I'm just going to label that overall energy change. Okay. It's much nicer when you can use certain symbols. Like for instance, at A level, we just put in that is the energy change. Okay. But there we go. All right, that's going to get you 3 fat marks. Bosh, bish, bish. Let's go. Or bish, bash, bosh. We're getting there, peeps. We're getting there. Right. I'm getting tired now. In the earth, most metals are found as compounds. Name one metal in the earth that's found as a metal itself. So if you went back in time in a time machine 2,000 years ago, you went walking around the UK, you went looking through the ground, looking along riverbanks, what metal would just be lying there, shining out at you? Now they show us most reactive to least reactive, and it's not copper. Copper we had to extract. I think it was from chalcopyrite, or I can't remember what copper came from, but some rock. Can you think of a less reactive metal than copper? Hopefully you can. Think of your jewelry at home. Okay, so you're looking at gold, you're looking at silver, potentially silver, but gold definitely. So I'm going with gold. I don't think we had a lot of platinum in England, but there we go, or in the UK. 5.2 suggests the most economical method for extracting metal X from the oxide of metal Z. Right, so what you've got to do, they're giving you this table here for a reason. If you wanted to get metal Z away from its oxide, so let's say I had metal Z oxide, and I want to remove the oxygen, I can do what's called a displacement reaction. Which of these metals in the table do you think could push metal Z away and take the oxygen? Which of these? Well, the nearest one to it is carbon. That's going to be the cheapest thing we can use in the table. Yes, potassium would react quickly and bust metal Z away and take the oxygen and leave you with pure metal Z. But it would be a bit expensive. So we're going to use carbon. And what we're going to do here with this displacement reaction, I don't know why I've written it like a thermal decomposition reaction. What we're going to do with this displacement reaction is go plus carbon, and that is going to leave you with carbon dioxide, because the carbon would steal the oxide, and its formula would be CO2, get carbon dioxide, and then metal Z would be pushed out on its own. And that's what they're saying. What's the best way to extract it? It'd be a displacement reaction, or you could say reduction with carbon. Carbon is taking the oxygen, it's reducing metal Z. So the two ways we tend to use are electrolysis and reduction with carbon. So I'm going to say reduction with carbon. I'm sure they'll accept displacement, but reduction with carbon sounds more sophisticated. Okay. 6.3, we've got figure 10 shows the electrolysis cell used to extract aluminium from aluminium oxide. So we've got these three electrodes. Don't forget to pause the video, have a go on a bit of paper, guys. Name substance X. Okay, I'm going to go through it. So metal wire here, positive. These are the positive carbon electrodes made of carbon or graphite. And this is the negative carbon electrode. And then what happens is the aluminium oxide is poured in here, and then the molten aluminium ions obviously get attracted to the negative and they fall down here. And the oxygen goes up here because oxide ions are negative with a 2 minus charge. They go and react with the positive carbon electrode and are dispersed there. But name substance X. So we added a molten mixture of aluminium oxide and substance X. You might know about this substance. It's one that lowers the melting point of aluminium oxide, making it more economical and cheaper to carry out the electrolysis. And if you don't know the answer to this, you should cry a lot. Okay, enough of my clue. It's cryolite. And if you don't get it right in your exam, you're going to cry. I know I say that joke a lot, but there we go. I say it a lot, but don't remember or don't forget cryolite. There we go. Cryolite. Okay, let's zing down. Enough of my beep poor jokes. 6.4, explain what happens to the positive carbon electrodes during the extraction of aluminium oxide. Well, I already kind of mentioned to you that aluminium oxide, Al2O3, is made of aluminium 3 plus ions. They're found in group 3. They lose 3 electrons. So when it's ionic, it's like that. And oxygen always has 2 minus ions. Now, the 2 minus ions, they go to the positive electrode here. So any of the oxide ions are going to go here to these electrodes. These are made of carbon. What do you think happens when carbon and oxygen react? You're going to get carbon dioxide. And that means carbon atoms are going to be stripped off of these. And eventually these are going to wear away and the reaction is going to stop. They erode or wear away because they lose mass. So 3 marks. Let's explain what happens to them. So as oxygen is discharged at positive electrode, oxygen reacts with carbon in electrode. We're gonna get down to Electric Avenue. Right, oxygen reacts with carbon in electrode, removes mass as carbon dioxide, electrodes erode or wear away. There we go, peeps. All done. 6.4 on the door. What we got? 6.5. The formula of aluminium oxide is Al2O3. Write a half equation for the reaction at the negative electrode. Okay, I kind of showed you aluminium is in group 3. So aluminium ions are going to be aluminium 3 plus. Yes, you're going to have two of them. We don't need to worry about that here. So it's say they're going to be attracted to the negative electrode, right? The aluminium 3 plus. In fact, it's not quite like that. They actually in, oh my days, normally in electrolysis it'd be like that, but in electrolysis of aluminium oxide, we make the bottom, the trough, the kind of container, we make that the negative electrode. So they go down here and they become aluminium metal, which we go to make aluminium foil that you wrap sandwiches in, window frames, all sorts. So anyway, you go like this. The negative electrode's always easy because you've got your metal ion. You just add the same amount of electrons to cancel out that plus. So 3e minus, 3e minus plus the 3 plus just leaves us with the Al because the E minuses take away the pluses. There's nothing left after that but the aluminium. And here we go. Okay. I think there's only one more question. Let me pause the video and have a shot of coffee. Okay. Excuse me while I wipe the coffee off my chin. Halogens, I'm just like a beast. Halogens are elements in copper 7 of the periodic table. 7.1, calcium reacts with chlorine to produce calcium chloride. Explain what happens to calcium atoms and to chlorine atoms when calcium reacts with chlorine to produce calcium chloride. Very common question in AQA. This is probably more difficultly worded, hence why it's question 7. Often they'll draw you the diagram and give you a little bit more clues, but it's the same question that they've asked many, 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 many times. So essentially you have calcium, right? What group is calcium in? In your periodic table, you should see calcium's in group 2. By the way, grab some paper and have a go at this. Calcium's in group 2, so it has 2 electrons in the outer shell. What group is chlorine in? Chlorine has 7, so I'm just showing the outer shell as it gets a little bit messy. Now, essentially, what's going to happen when these two bad boys react, calcium and chlorine? They're going to get together in an ionic compound because calcium is a metal and chlorine's a non-metal. But look, I guess you've worked out what's going to happen, right? Calcium is going to shift an electron over there, but now calcium's still lonely, right? Lonely. It's just got one electron doing nothing. So what it needs to do is find another chlorine atom, which is going to become a chloride ion. And it's going to do that by giving the second electron away like that. Now, all we need to do is put what I've just done in words. And so we want to be very specific. Calcium gives away 2 electrons to chlorine. Now, that will get you 2 of the 4 marks. 1 for saying that calcium loses electrons and 1 for saying that it's the chlorine that gets it. Now we need to be specific. Each chlorine gets 1 electron. Now, obviously, if you've done my funky diagram, the examiner's going to be like, yes, this person knows what they're on about. So don't forget, they will mark diagrams if you show, you'll get some marks from just doing the diagram if you can't explain it. Okay, so each chlorine gets 1 electron. What else can I say? Ca is now a Ca2 plus ion. Oh my days. So this is going to become a 2 plus ion and Cl becomes Cl minus ion, right? I know I've not used the right capitals there, but there we go. So I've now said it's a calcium ions, chloride ion, and I'm going to add in something extra because sometimes on the mark scheme, they all have full outer shells. So, and you know, I could, if I want to get really sexy and exciting, and I don't, I could put the new electronic configurations. So calcium's gone from like 2882 to 288. And chlorine's gone from like 287 to 288. They've both ended up with the same electronic structure, funnily enough. Okay, so you could put that in there if you wanted to get real funky and you think you're like, Emily Elephant, like clever clogs, whatever it does. I've been watching Peppa Pig with my daughter. There we go. 4 marks. Boom. Let's go. My elephant noise wasn't good. Explain why chlorine is more reactive than bromine. Okay, so this is the same question you can get about group one. They could say, why is potassium more reactive than lithium? Why does chlorine react faster than bromine? All of those mean the same thing. But essentially, with group seven, as you go down, in fact, with all groups, with every group, as you go down, they get bigger. So as we go down from bromine to chlorine in the halogens, they get bigger. Now, what is it that we just looked, what are halogens trying to do? When they react, what is it that they want to do? They want to take an electron, right? I've done this the wrong way round, so smack myself in the head. Oh! Okay, so chlorine is above bromine. Bromine's the bigger, fatter one. Okay, so why is chlorine more reactive than bromine? That would make sense, wouldn't it? Okay. Just smashed myself in the face. That was painful. Okay, so think about it. They're halogens, they're group sevens, they're trying to steal electrons. Why is it easier for chlorine to steal an electron than bromine? Think about what's going on in the middle. Think about what electrons are charged with and see if you can construct an answer for 4 marks. Have a go. Okay, I'm going to go through the answers. So we want to say chlorine is smaller. Now you could say bromine is bigger. It's up to you how you word this. Chlorine is smaller than bromine. It is trying to gain an electron. So it wants to gain an electron. The outer electron is closer to the positive nucleus, so more attraction to the nucleus. Now, here's a bonus one. Although I didn't show it here, obviously, bromine has more shells. I'm not showing you the correct number, but bromine has more shells than that. So we can say chlorine has less shielding. And this is just something that comes up on the mark scheme for these type of questions and with the group one ones. So less shielding means there's less kind of walls in the way blocking the attraction of the electron to the nucleus. Okay, so all of those are going to get me more marks and lovely jubbly. Chlorine is smaller, it's trying to get an electron. The electron's closer to the nucleus, there's greater attraction, there's less shielding. We could say a greater electrostatic force of attraction if I wanted to get real cool about it. Electrons are negative, the nucleus is positive, electrons are attracted to the nucleus, chlorine is smaller. It's more easy to gain, it more easily gains the electron, more easily gains the electron, or takes less energy to gain the electron. That's another marking point. All right, folks, we've got to be nearly at the end of this one. Oh my gosh, we're not. I'm so tired as well. 7.3, table 4 shows the boiling points of the hydrogen halides. We've got hydrogen fluoride, hydrogen chloride, hydrogen bromide, hydrogen iodide. I think this is the worst question in the whole paper. So if you block this question, don't worry. You only need about 70% to get a level 9. And this question is pretty messy, really. Describe how the boiling points of the hydrogen halides change as the relative formula mass changes. Essentially, as they get bigger, the boiling points increase. They're getting closer to 0. Okay, this is an exception that you don't really need to talk about. You don't really need to know at GCSE why, but it's kind of confusing that they put that there. So I would say the boiling points get larger as the RFM increases. So as the relative formula mass increases, the boiling points get bigger. And that is the general term. And then I would just point out the exception. However, hydrogen fluoride has the highest boiling point and yet has the lowest RFM. So there's an exception. That's actually to do with something called hydrogen bonding. And yeah, so it has an unusually high boiling point than it should do for its size. All right, let's move on. Basically, its weak intermolecular forces are stronger than the molecular forces between the others. Okay, and it's because of this thing called hydrogen bonding. You learn that if you do A-level chemistry. Question 8, carbon nanotubes are cylindrical fullerenes. Figure 11 represents the structure of a carbon nanotube. Describe the arrangement of carbon atoms in the carbon nanotube. So we can see they're in a single layer. So carbon atoms are in a single layer. Carbon atoms in a single layer. And if we have a little check, how many bonds are around each carbon atom? And it's three. So each carbon atom is bonded to three others. And they look like they're in hexagons. I don't know if there's any pentagons there, but they look like in hexagonal shapes. Now, I know it's 1 mark, but I'm putting everything down. And it'd be interesting to check the mark scheme, see which ones of those are on there. Okay, excuse my spelling. 8.2, carbon nanotubes are used in electronics. Give one other use of carbon nanotubes. So they tend to have a high tensile strength. We can say medical in delivery of medicines, high tensile strength in sports equipment. I believe they use them in sports equipment, like tennis rackets, the handles and the frames. Anywho, I know they use nano cages in medicine. I'm not sure about the nanotubes, but we'll put that there. It's probably on the mark scheme. So, okay, a nanotube contains 2,380 carbon atoms. That's not actually a lot when you consider that 1 mole of carbon contains 6.02 times 10 to the 23. So just to get this in your head, right? Um, that is Chase. That is 602 and then 23 zeros, right? So can you imagine 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23? That is a big number, right? That's not 6 billion. That's not 6 trillion. That's not 6 quinzillion. That is Avogadro's constant, right? If you had that much money in the bank in pounds, you'd be the richest person in the universe, let alone, you'd have like trillions more money than Elon Musk and Vladimir Putin and everybody else that's wealthy, Bill Gates put together and the Sultan of Brunei and whoever else, right? That is serious wonga. So that's a massive number. And they're saying that's how many particles are in 1 mole. How many carbon atoms are in this nanotube? How many moles of carbon is that? Well, that's going to be a tiny amount because we need to do 2,380 divided by that big fat number. Luckily for us, we have that button on our calculator, so we can just put times X and then write 23. You'll see at the bottom of the calculator, you've got a X10 with a little X in the top right corner. That's the button you use. So put in 2380, then put divided by, then put 6.02, and then put that times X and then 23. And then you'll get your answer. So I need to go ahead and do that now because while I was saying that, my calculator was switched off because I'm a dope. All right, I got 3.954 times 10 to the minus 21. So 3.954 times 10 to the minus 21. So that's 21 zeros in front of the three. It's a really small amount of moles of carbon. Explain why carbon nanotubes conduct electricity. Refer to bonding between carbon atoms in your answer. So what I need to say is each carbon, we already said this earlier, each carbon atom is bonded to three others. What does that mean? Well, carbon's in group 4. It has an extra electron for each carbon atom. This forms a sea of electrons or delocalized electrons. These delocalized electrons can carry charge through the structure. Okay, now I can't spell, or it's really that I've got fat fingers. I need to go on a bit of a diet. There we go. Okay, and so I'm always hitting more than one key when I try to type. Boom. Oh my days, come on. Come on, I just want to roll down. Was that it? Hey, we finished it. Guys, it massively helps me out if you hit the like, share, subscribe to the channel, tell your friends. This is the way to get an A. Boom, boom, boom. If you start watching my videos and all my walkthroughs and you're in year 10, you're getting an A star. You're getting a level 9. You're going to get a result that is so fine that when you come home, everybody you know is going to burst into tears when they hear what amazing science results you got. So make sure you subscribe, you share, you like. You know the coup. Let's get to the marks.
You're still here? It's over.